Yeah, Pythagorean theorem is our a squared plus b squared equals c squared. And it only is really for a right triangle. So we're only looking at our right triangles. And when we have a right triangle, we have, I'm trying to get that mouse off of there, but it's not moving. Okay. We have a hypotenuse. Now the hypotenuse is always the side that's across from the right angle. It's the slanted side, or you can think about it as the side across from that 90-degree angle. And the other sides of my triangle are called the legs. These are the legs of my triangle. And so the important piece with the Pythagorean theorem that students sometimes do incorrectly is that A and B have to be the sides that are legs, and C has to be the hypotenuse. Okay, so it always has to be the input that is equal to the hypotenuse squared. And with the Pythagorean theorem, given any two sides, of a right triangle, you can find the third. Really, this entire unit is about right triangles. We don't always have two sides. Sometimes we're only going to be given one side, and that'll be a little further into the unit. But if we're given two sides, we can always use the Pythagorean theorem to solve. Okay, even if it's a special right or it's something funky going on, we have two sides. We can find a third using this formula: a squared plus b squared equals c squared. So before we get into some kind of stuff beyond just the theorem and using the equation, let's do our warm-up. So the warm-up, we're now going to use that a squared b squared equals c squared. We've done it before. Okay, and look at a few examples. Now, some of these have radicals, so I'm just going to write an example at the top. If I had like the square root of 5 and I squared it, it's just going to become 5. They're inverse operations. So if I'm putting in a radical, it just really cancels each other out in terms of the a squared, b squared, c squared stuff. Okay, and you'll see that, and we're going to go through these in a minute. Okay, give me a minute to kind of work through these 6 triangles, and then we'll go from there. These are my legs, and this is my hypotenuse. So the setup is that I just have my kind of given values squared equal to my unknown. And then on 2, same idea, I'm given, these are the legs of my triangle. But then on 3 and 4, so let me show answers now for 3 and 4, I have a leg. So if these are my legs, I have a leg that's missing. And then I have, this is my hypotenuse. So looking at 3, I have the square root of 11 squared plus x squared equals the square root of 14 squared. The hypotenuse we know. And then, like I said, those just cancel each other out. So it just leaves me with 11 and 14. And then I have to solve to get x. So I subtract 11 from both sides and then take the square root to solve for x. Same on 14. I'm given 14, the numbers are kind of hard. I'm given my hypotenuse in one of my legs. So I have 13 squared plus an unknown squared, x squared, equals 15 squared. And I have to actually solve for x. So I subtract my 169, get x squared equals 56. And then to get from x squared to x, you take the square root. Brings me to x equals the square root of 56. That breaks into 4 times 14. and I can simplify that radical. So just be careful in terms of what you plug in where. Okay, the sides have to be here, hypotenuse here. And again, the hypotenuse, we know if this is my 90 degree, the hypotenuse is always across from the 90 degrees. So that's how I know which side in that triangle is considered the hypotenuse or should be on that right-hand side. Okay. And I'll give you a second to look at 5 and 6 if you had that switched around. Initially, kind of set up correctly in order to solve and get the right answer. And 80 is a little bit tricky. A lot of people go with 4 and 20, which isn't necessarily wrong, but 20 still has a perfect square in it. So I can actually take 80 and break it into 16 times 5, or a totally simplified rad would be 4 rad 5. Same on 6, where I'm given a leg and the hypotenuse, so I have to do some solving, and I get the square root of 200, which is 100 times 2. Square root of 100 is 10, so that's how I get to the 10 rad 2 for my final answer. Let's, before we go back to notes, flip back to the homework from last night, which is the page before. I just went through and simplified, but I want to talk about the addition and subtraction stuff. So, and some of these were tricky, like what I did is I used, so you can't use a calculator to be like, oh, what's the square root of 128? That's not going to help you. You don't want like this weird decimal. But what you can do if you really get stuck and you're working on simplifying a rad is start dividing that 128 by my perfect square numbers, or like this one was a little tricky. I had to think about how what number is going to go into that. So if I go 252 and I say, okay, well, can I divide it by 4? Okay, so 4 works, but I could see that I still had a perfect square inside of there. And so then I kept going and I was like, well, what's a multiple of 4? That's going to go in there. So then I go, well, 252 divided by 16. Okay, what about 252 divided by 64 is another multiple of 4. So I'm just dividing by, oops, what did I do? I went too far. 252 divided by, I skipped 36. I'm just dividing by perfect squares. 4, 16. We know 25 doesn't fit into there. 25 is an easy one to see because it's like either a 5 and a 0, right? Until I find one that is dividing in and also the largest that divides in evenly. So I kind of just take my number and start thinking about, well, how does that factor out? And then using 36 and 7 there. And sometimes it takes a little bit to think through. So let me show you kind of what I have here. I'll move this down in a minute. You can check your own work. Hopefully this is submitted, ready to be graded tomorrow. I try to get most homework updated on Wednesday. If you don't have it in there yet, make sure it's in there by tomorrow. Actually, sometimes I might look at it next block even. Moving this down. This one is also a tricky one, 49 times 6. Okay, let's talk about the addition subtraction problems that were on the homework. So when we're adding and subtracting with rads, first thing we want to do is simplify. So, and these coefficients are just going to kind of come along for the ride at first. So I'm going to have 3 times whatever the square root of 45 simplifies into. So what perfect square number goes into 45? 4, 9, 16, 25, 36. What number goes into 45? 9. 45 is 9 times 5. Now I don't have to write that in between step. I know the square root of 9 is 3. Okay, or the square root of 45 becomes 3 rad 5. So I evaluated that perfect square. Plus 3 times, and then simplifying 18 again is 9 times 2, so becomes 3 rad 2. Plus, and I can't simplify 2 rad 2 any further. Okay. So then, let's see, I have 9 rad 5 plus 9 rad 2 plus 2 rad 2. So all I'm doing there is I'm taking the coefficients that were out front in the first place and multiplying it by whatever I end up taking out of the radical. And I can only combine things that are the same rad. So I can take 9 rad 2 and add it with 2 rad 2, giving me 11 rad 2s. And this is just going to still be 9 rad 5. I can't add those together and make it a single term. I'm just leaving them as two separate terms there. Okay, so there's 9. Same idea on 10. So I still have this 2. I know that 27 is 9 times 3, or simplifies to 3 rad 3. Notice how I'm careful to put multiplication in between. Before I had put it there, it looked like 23 rad 3, and then students make the mistake of miscalculating what you have there. Okay, this is 2 times 3 rad 3. This will be 3 times, 12 is 4 times 3, 2 rad 3, plus 3 times, same idea, 2 rad 3. Okay, so for all those rads that I simplified, let me get on the screen. Those coefficients get multiplied by what I simplified by. So 6 rad 3 minus 6 rad 3 plus 6 rad 3, right? So these will cancel, and it will leave me with just 1 6 rad 3. $11, this one stays the same. What perfect square goes into 27? Either has to be 4, 9, or 25. 9 times 3, or 3 rad 3, plus 2 times 3 rad 3, cleaning that up. 2 rad 3 minus 3 rad 3, plus 6 rad 3. They are all like rads, so I'm just adding up their coefficients. So I'm going 2 take away 3 is -1, plus 6 is 5 rad 3s all together. I'm really just adding the numbers out front together. And 12, let's see, you would have had -3 rad 3 minus 2 rad 5 plus 3 times 2 rad 5. You would have had 4 rad 5s. Can't combine the 3 rad 3s and the rad 5s. That would have been 10, or 12, sorry. Okay, so hopefully we're feeling somewhat confident with our rad stuff. Again, the further we get, like say Thursday, Friday, we're going to be using rads quite a bit with solving for some triangles. So we need to have that skill pretty solid in Algebra 1. So now we looked at the Pythagorean theorem. Okay, we wrote down, here's our Pythagorean theorem. Now let's look at this triangle that it gave us down below. So what do I have there? Like, do I have both legs, a hypotenuse and a leg? What? I have a hypotenuse and a leg. So this guy right here is my hypotenuse, right? And here's a leg. We'll call this X. Here's my other leg. Okay, so in terms of substituting that into a squared plus b squared equals c squared, again, we need to make sure these are legs. That's the hypotenuse. We would have 3 squared plus x squared equals 5 squared. We have a leg and a hypotenuse. Somebody asked, does it matter how I put the legs in? No, I could have also written x squared plus 3 squared. That's fine. Okay, addition, it doesn't really matter what order I write them in. 3 squared is 9 plus x squared equals 5 squared is 25. How would I solve for x from here? What would I do? Subtract 9, which gives me x squared equals 16. To undo this being squared, I take the square root. What's the square root of 16? 4. So our missing side here is 4. What's unique about this triangle is it's what's called a Pythagorean triple. Okay, we're looking at Pythagorean triples. 3, 4, 5 is a Pythagorean triple. An example of a Pythagorean triple. A triple happens when all 3 sides of a right triangle are integers. Integers meaning there's no square root or decimal as part of either my legs or my hypotenuse. Okay. Why do we care about triples? Well, if I memorize a few of them, I don't have to use the Pythagorean theorem. Like, for example, because I know 3, 4, 5 is a triple, if I was given this triangle to solve, I would go, oh, well, it's 4, because it has to follow the pattern. It will always go 3, 4, 5. If I had 4, 5, I would know the other side is 3. Now, what's important about a triple, similar to the theorem, is that it is always that the largest side is the hypotenuse. So it wouldn't work. Let me give an example. So for example, if I knew this is 5 and that's 4, then I go, oh, this is 3, because it has to be 3, 4, 5. But if I was given a right triangle that looked like this, and I was told 5 and 4, this side is not going to be 3. It's not going to be an integer because 5 is not the hypotenuse. Does that make sense that that largest side has to be the hypotenuse side? It can't be a leg. That's going to be different. It's going to give us a radical answer there. Okay. So this is kind of a new way to think about our right triangles. We don't necessarily need the theorem if we know a few of these triples. Do you have to memorize the triples? Not really, because the theorem worked, right? I could still have known that that was 4 by using the Pythagorean theorem. It just kind of speeds you up. It makes you more efficient at solving for triangles. So flip this over. Now you get to do some more Pythagorean theorem on your own here. So what we're going to do before talking about how we really use these is we're going to fill in this table. So in this table, notice it has A, B, and C. So A, B, these have to be legs. And then this is my hypotenuse. So this is the one we just solved for. We know that 3, 4, 5 is a triple. All of the rest of these will also be triples, but the place the missing piece is, or X is going to be in your Pythagorean theorem, is going to change depending on what part's missing. Okay, like for example, on the first one, it asks you to find your hypotenuse, whereas here it asks you to find a leg, a hypotenuse, a leg. So we're going to use the Pythagorean theorem. Let me just give you an example of this first missing piece, where we're going to say leg squared equals hypotenuse squared, and we're going to fill in our table of other triples that exist. So I would go, okay, this would be 25, this one 44, which is going to give me 169. Take the square root, gives me 13. Okay, so another triple is 5, 12, 13. But when I set this one up, X is going to be a leg. And if you need to use a phone, or I can go get calculators, actually, that might be helpful today anyway. I'll go get calculators. Okay, so what I want you to do is use the theorem right now, because we don't know our triples yet, and find all the missing pieces here. Okay, and then we'll look at how this looks when we apply it. 15, 17. What do you think? 8, good, yeah. 8, 15, 17. Then I have 9, 40. This one would have given us a large number, so let's maybe look at this one. 9 squared plus 40 squared equals what squared? So 9 squared, 81. 40 squared is going to be 1600. So I'm going to have 1681 equals x squared. And to get x, we need to take the square root of that. So again, in our calculator, second x squared, 1681, enter, gives me 41 for my third side of that triple. Give you 30 seconds to fill out this last one. We're missing a leg. So setup would be x squared plus 60 squared equals 61 squared. Give you some time to use those calculators. Yell it out if you know it. 11. Yep, agreed. Now, do I even know all of these by heart or really care to know all of them by heart? Not really. My suggestion to you would be to definitely have these two down. So I think the first two it just makes you more efficient. It makes you a little faster at math, saves you time. So if you know the 3, 4, 5 triple, which is our first triple, and the 5, 12, 13 triple, you will be able to solve more triangles. And actually, there's infinitely many triangles related to that first one. So, meaning that I have my 3, 4, 5 triple. Oops, wrong way. Okay. Multiplying each number in the triple by the same amount is going to give you a new triple. So for example, this 3, 4, 5 triple, if I multiply it by 3, if I multiply all of them by 3, it gives me 9, 12, 15. Is 9, 12, 15 a Pythagorean triple? Well, 9 squared plus 12 squared, is that going to equal 15 squared? 81 plus 144 equals 225, right? Give me a moment. Yeah, 225. And 144 plus 81, boom, gives me 225. So yes, 9, 12, 15 would be a triple. 9, 12, 15 is a triple because 3, 4, 5 is. So if I know that 3, 4, 5 is a triple, I know 3, 4, 5. Guess what I also know? If I multiply them all by 2, I know that 6, 8, 10 is a triple. Multiply them all by 3, I know that 9, 12, 15 is a triple. So I'm going to here, to here. I could multiply it by 10. And if I had 30 and 40 for two sides, then I know the third side would be 50. Okay, so I can use triples to find all of these triangles that before I would have had to go through a formula to find. I can just plug in the third side. Any multiple of 3, 4, 5 is also going to be a triple. So let's look at 5, 12, 13. If I know 5, 12, 13, if I have that memorized, what would be another triple based off of that one? What would be another triple based off of that triple? 10, 24, 26, good. And all we did there was multiply it by 2, or I could multiply it by 3 and say 15, 36, 39. Okay, that would also be a triple. So I can find all these additional values. And like I said, I only really focus on the first two. That's enough to speed me up a little bit if I happen to stumble on another one. Sometimes 7, 24, 25 is pretty easy to spot as well. But I think, and even if you just had the first one, it's going to help speed you up a little bit. So if we flip this page, just gives us a few examples. We're not going to fill this one out. Okay, it shows us why this Pythagorean theorem works. Gives us some triples, and it just kind of gives us some multiples. So kind of this table, as you're doing your work today, and possibly homework, I think you'll finish it in class today though. These tables, here are the first two, just kind of some to notice, right? So times 3 times 4, or times 2 times 3 times 4 times 5. If I know 3, 4, 5, I know all of these and infinitely many beyond that. If I know 5, 12, 13, I know all of these and infinitely many beyond that. Okay. We don't need to do this bottom part right now. So what you're going to do in your work today, first it still starts with radicals. So the first top part is simplify, and it's multiple choice, and you're finding which one matches it. Now on the top part of this work, it has a coefficient in front of it. So when I simplify the square root of 18 and say, well, it's 9 times 2, I'm going to have a coefficient in front of it still. So that just means that in the end, I'll have 6 times 3. Okay, so it's going to be 18 rad 2. Okay, so that coefficient is just adding a piece where you're going to have something you're going to multiply by in the end. Okay, simplify the rad, multiply those coefficients out front. So it starts with simplifying. Then it goes to find the missing side. And it's challenging you to try to identify triples. So look at the triangle and decide, do I have a triple here? If I do, I'll use the triple, and then you just write the answer. You don't have to do any math, you just write the answer because you know that it's a triple. If it's not a triple, then you can use the Pythagorean theorem to solve. Okay? Does that make sense, what you're doing right now? So this is homework 35. Let's talk about, before you work, so don't start yet, I want ears listening. Tomorrow we are Zooming, so we had a few weeks that it made more sense to just let you work than having to meet. Tomorrow we are going to take notes, okay? The notes that we're doing tomorrow is on the quiz that, let me double check the front of our thing. We have a quiz Friday, but I'm not sure if I'm having you guys take it Monday. Can't remember. I'll check. We have a quiz that's on this beginning stuff, so simplifying rads, and the Pythagorean theorem. And that's basically it. But tomorrow we talk about something called the converse to the Pythagorean theorem. So you need to Zoom to get those notes. And then for work tomorrow, you're going to do a checkout that's basically going to be what the quiz is. Okay, where we already know how to do the first part. We already know how to do the second part. What's at the bottom of that checkout, your work for tomorrow, you can't do if you don't show up to Zoom and you're there for the notes. This is what our notes are. Okay, so you have to Zoom tomorrow, get the notes, so you're ready for your quiz, and you'll also be ready for the checkout for tomorrow, what you need to submit in classroom. Just one page. Yeah. You have it, it's actually in there. Like you could start it, you could do the top half even if you had extra time today. What you won't be able to do is do the bottom half till tomorrow. Sure. Okay, so just make sure you have that in your mind to Zoom in tomorrow. And then you'll just have that one page to submit.